Good morning and welcome. This is the Research Papers Competition sponsored by the MLB. And my name is John Kendall, and I'm on the Sloan Research Papers team. And it is my pleasure to introduce Raghav Singhal, who will be presenting how to play strategically in fantasy sports and win. The presentation will last 20 minutes, after which we'll have a 5-minute Q&A session. And during that Q&A session, if you have a question, please raise your hand, and we will provide you with a microphone. And now, please join me in welcoming Raghav Singhal.
Thanks, John. Good morning, everyone. It's a pleasure to be here. As John said, I'll be talking about how to play strategically in fantasy sports. This is a joint work I did with my PhD advisor, Martin, who now is at Imperial College. I'm a PhD candidate at Columbia. Okay. The agenda for today, there are these bullet points, but at a high level, what I'll talk about is I'll introduce the problem, which most of us should be familiar with, what fantasy sports are. Then I'll talk about how we go about solving it. That's the middle 2 to 3 bullet points. And finally, I'll talk about the results. Okay. Introduction. As most of us know, fantasy sports is a multi-billion-dollar industry. There's millions of annual users on 2 major websites. That's DraftKings and FanDuel. And it involves real money. And quite interestingly, it has been in news recently for various reasons. This is an article from New York Times in 2015, which actually led to New York State banning fantasy sports for a few months. And the exact issue was the issue of insider trading, where the employees of fantasy sports websites were accused of using insider information to place their own bets. So before we present my model, I'll like to discuss what the existing work is in this area. There's only one work that we know of, and that's by Hunter, Vielma, and Zaman here at MIT. What they do is they approximate the payoff structure of how you win money in fantasy sports by winner takes all. So what that means is they assume that the person who comes first in the contest takes all the money, and the other people get nothing, which is not true in reality. And also one of the key drawbacks which we believe they have is they do not consider opponents' behavior. In fantasy sports, we believe it's important that you should account for how your opponents are behaving. For example, say if you perform good, but if opponents perform better, you might lose everything. On the other hand, if you perform bad, but if your opponents perform worse, you might still win. So our contributions are pretty much, we provide a coherent framework for optimizing DFS portfolios. We model the exact payoff structure, and we maximize the expected reward. To that extent, the key aspect, as I mentioned earlier, is that we explicitly account for the model, the opponent's behavior in our model. And as we'll see later on, that this model actually helps us to evaluate the value of insider information, which has been in the news recently. Okay. So now I'll jump to the mathematics of fantasy sports. I'll try to keep this low on math, but the next few sections will have some math till we get the results. So there are athletes, the real-world players, say football players. There's P of them, and there could be 100 to 500. And what we care about is how they perform, their fantasy points. So by delta, that's my vector, contains the fantasy points of all the real athletes. Okay? And I'll assume that we know how, in expectation, what the fantasy points they'll score, and their variance-covariance matrix, sigma delta. As a decision maker, that is a fantasy player, my decision is to construct a portfolio. And that is my vector W, which if the ith component of W is 1, that means I choose that player. If it's 0, that means I do not choose that athlete. And if you give me my portfolio and the delta, the realizations of athletes, I can compute my fantasy points. That's points total. That's just a dot product. Also, we note that in reality, you can submit up to n portfolios. Usually, n is 1 or 50 or 100. But for now, we'll just focus on n equals 1. In our paper, we discuss the extensions to multiple n. Okay. Coming to our opponents, their O opponents could be as low as 1, could be as high as 500,000. And they have their own portfolios. And we denote the collection of all those portfolios by WOP. And we can, in the same fashion, compute their fantasy points. Some more basics. There are reward structures in fantasy sports. It could be either double up or top heavy. In double up, the simplest example is, say you pay $1 to participate, and if you come in the top 50%, you win $2. You double up. Okay? Top heavy is a bit more extreme in that the ranked 1 portfolio could win as high as $1 million. Rank 2, maybe it declines exponentially. I mean, by the time you reach the 30th percentile, you won't be making much money. So our main focus for real-world experiments is top-heavy. But in the interest of time, I'll present the double-up theory, because it is a special case of top-heavy. And in our paper, we discuss how the results extend under some mild assumptions to top-heavy. Okay. So now the actual mathematical optimization problem we're tackling in the double-up scenario. Okay? So before I write down the optimization model, I'll define a key quantity that's a stochastic benchmark, GR. It's essentially the benchmark you want to beat. So recall that GOs are the fantasy points of my opponents, and there's O of them. And what I care about is I want to, say, beat the 50th percentile of my opponents, for example, right? So GR essentially captures that. It's a random variable that depends on how my opponents behave, and it depends on how the real-world athletes perform. So it depends on both delta and WOP. And essentially, my optimization problem, that is, I want to maximize my expected reward, which actually can show is equivalent to maximizing the probability you win. Okay? And by win, we essentially mean that our fantasy points, W transpose delta, beat the stochastic benchmark. If that happens, we win. As you can see, it's probability of exceeding a stochastic benchmark. For those of you who are familiar with the optimization literature, it's a non-trivial optimization problem. There's no closed-form analytical solution which you can use to solve this problem. Before I discuss the solution, what I'll do is I'll spend some time discussing the uncertainty that comes from opponents, that is their behavior, WOP. Okay. So recall that benchmark depends on opponents, so it's important to predict opponents. So what I'll do is I'll explain via example how this works. So let's consider football, and let's say my opponent is picking quarterbacks. I'm considering a random opponent, and let's say there are 4 quarterbacks. Okay? So we assume that my random opponent will pick quarterback K with probability Pk. Okay? Now, to begin with, I don't even know what this probability is. It itself is random. Okay? So what I do is I go a step beyond and say that this probability is random and it's being generated by the Dirichlet distribution. This part is a bit technical, and there's a parameter alpha. And finally, what I really want is intuitively I expect that if, say, Aaron Rodgers is expected to play very well and his cost is really low, this probability should be high. It should be somehow linked to these features. So we provide that link via alpha and a link function where x denotes the features of the athletes. All that remains in this equation is to estimate beta, which we do weakly using real data, using Bayesian modeling. There are a few technicalities I'm skipping here in the interest of time, but in our paper, we extend this approach to actually make it tractable and really feasible. Okay. Just before I present my main result, this is just a result for my prediction of opponents. Okay. So this is real data. It's a contest on FanDuel in the week 10 of the recent football season. On the x-axis, you're seeing the quarterbacks that are available on that week. The font is a bit small. On the y-axis, you're seeing how many fantasy players picked that player, that quarterback. Okay? The first thing you'll observe is that outlier corresponding to Matt Stafford, somewhere in the middle. He was the most picked quarterback. Around 20% of the players picked him. And a model actually did a fairly decent job at predicting that. Okay. Related to this point, you'll see is that our 95% intervals pretty much contain 95% of the data, which is an indication of a good predictive model. Finally, you'll also see that there are some cases where we miss out on predictions. Specifically, if you look at the case of Ben towards the right, he was the second most picked quarterback that week. Around 15% of the opponents picked him, but we underpredicted him. So this happens. I mean, we'll be right 95% of the time because by definition, these are 95% intervals. Okay. So now I introduced the optimization problem that I want to solve. Now I know how to tackle my opponents. Now I'll talk about how do I go about solving this optimization problem. How do I maximize the probability I win? Okay. So recall our optimization problem is there. I want to maximize the probability I win. I'll use a simple trick. I'll restate this problem as maximizing a random variable being positive. So y is a random variable, which I defined appropriately. I just shifted the right-hand side, the g on the right-hand side to the left, and that's how I defined y. And it's an equivalent maximization problem. Now I go one step further, and I assume y is normally distributed. I note that this is not a key assumption in the sense that our framework still goes through, but then it's mostly a heuristic. For the technical results to go through in math, you need this assumption. And now we import the theory from financial engineering, where such problems have been widely studied, and we use that theory to compute the optimal portfolio. And actually, you can show that the portfolio is globally optimal. That's the best you can do if you want to maximize your expected reward. For that, we use something called binary quadratic programs. It's more technical. Okay, just to, instead of talking about the proof or the math behind this, what I'll do is show you the intuition behind how our algorithm works. So recall the problem is to maximize probability a normal random variable exceeds 0. So what I've done is I've plotted a normal random variable. There's a 0 in the middle. Okay? And let's say there's case 1, where I know that there exists some portfolio for which the portfolio mean is above 0. So in this case, the intuition tells me that if I want to maximize the blue area, that's a probability I want to maximize, what I should be doing is I should be trying to push my mean to the right. That's how I'll increase my area, blue area. That's what I do. And at the same time, it also tells me that I should shrink my width, my variance. Okay? Because in this case, I'm already above the mean. I don't want to be taking risk here. On the other hand, that's case 2. If there's no portfolio with which I can exceed the benchmark, that is 0, intuition again tells me that I should still be trying to slide my mean to the right, because that's how I'll increase the blue area. But now, in this case, I should also be expanding my width. Okay? And actually, you can go about mathematically and prove this actually works. Okay. So we've talked about what the problem is, how we go about modeling opponents, how we solve it. One thing I waved my hands on is some of the input parameters that go inside the optimization model. In particular, what I would like to discuss is estimating those parameters even tractable. Because if it's computationally intractable, there's no point of doing all this fancy math. I mean, we can just call it quits. Okay. So here's the thing. Recall that I have 2 underlying uncertainties, how the athletes perform and how my opponents behave. That's delta and WOP. What I'll do is I'll generate Monte Carlo samples. I'll use simulation techniques to generate a lot of samples of them. And using these samples, I want to estimate the parameters I'm interested in. But the key challenge here is that, recall, the number of opponents could be as high as 500,000. So sampling from 500,000 opponents is very challenging. It takes a lot of computation time. And on the other hand, there's another observation that I only need my opponents in order to predict my benchmark. So if somehow I can efficiently predict my benchmark, I don't necessarily need to deal with 500,000 opponents. So here's what we do. We import some heavy machinery from the theory of order statistics. I won't be explaining this equation in detail. Essentially, what this does is it allows us to sample the benchmark using just one random opponent instead of 500,000 random opponents. Okay. The underlying assumption behind this equation is that the number of opponents is really large, which in our case is actually true. It's 500,000. And to begin with, if the number of opponents were not too large, you could just sample naively. You didn't need this heavy machinery. Okay, so we're done with all the math. Find the results. So we participated at FanDuel in the recent NFL season. Our main focus, again, is top-heavy. And we needed some benchmarks, so we used the benchmark that exists in the literature as a model to compare with. Is our model, is doing all this fancy math even worth it? Okay. So what we'll do is each week there's a contest. We'll invest $50 from our model, that is a strategic model, and we'll invest $50 from the benchmark model and see how they perform. So at the time we submitted this paper, 12 weeks had evolved in the football season. So I'll be presenting the result for 12 weeks, but I'll also mention the complete season results, and they're also in the appendix if you're really interested in how that evolved. So here's the evolution of our profit and losses. So x-axis is the week 1 to 12. Y-axis is our cumulative profit. Okay? Black line is our strategic model, and blue is the benchmark. As you can see, we had a return of investment of over 500% in just 12 weeks. And also, we did a lot of simulations using our stochastic models. And those simulations tell us that in expectation, the strategic model is expected to earn 5 times more than the benchmark model. So essentially, this tells you that going this step further, using all this math to modeling your opponents is actually worth it. We also would like to point out that there's a huge variance issue, especially in football. I'll touch on this issue in a couple of minutes when I discuss ongoing research. Out here, I just want to highlight the standard deviation that you're seeing. So this is, again, the same plot as before, but I just added the standard deviations. As you can see, that there's a pretty good chance that we could have made over $5,000 or even lost some money. That's because the variance of these portfolios is super high. And that's how fantasy sports work. You invest some money, you could lose it all, or you could go big. But the whole point is in expectation, if you're making money and you play long enough, you might win. Also, just to be completely transparent, for the complete season, the regular season, that is 17 weeks, our ROI was 350%. It fell down a bit from 500%, whereas the benchmark was 50%. We were still 7 times above the benchmark. Okay. So finally, conclusion. We developed a new framework for portfolio construction in DFS. We accounted for the behavior of opponents explicitly using the Dirichlet multinomial data generating process. We imported some theory from finance and showed the solution satisfies some nice mathematical properties. And we played real-world contests. Okay. Some ongoing research. The first point relates to the high variance issue I just discussed a couple of minutes ago, is that we believe there's a big, in NFL, there's high variance. And the reason for that is NFL is prone to more injuries. And there's a big roster size, so there's uncertainty in which player will be playing on the field and which player will not be playing. Okay? And in addition to that, you add the factor that there's only 16 games per team in an NFL season. So if you have a lot of variance, theory tells you for things to average out, you need more data points. But here you have high variance and less data points. So it's hard for things to average out. The second ongoing research is the issue of updating your parameter estimates dynamically. So a lot of us know that the way sports work is 1 or 2 hours before the actual game is about to begin, a lot of news comes out. And we believe this news is key For example, if news comes out that player A will not be the main running back, whereas player B will be the main running back of the team, this has a direct implication of what's the expected fantasy points of those players. So if one can update those parameters dynamically, that would really boost your P&L. Third is the issue of insider trading, which I mentioned in my initial slides. So in our preliminary experiments, what we saw is a fairly intuitive result. Say there's a fantasy player who's not strategic. For that fantasy player, if you provide him the information, the insider information about how the opponents will behave, that information is super valuable because to begin with, she was not being strategic. Okay. Whereas on the other hand, if she was strategic to begin with, using some sort of predictions of opponents, and then you give her the insider information, for her, we saw that the value of insider trading was not too much, which intuitively makes sense. If you're already predicting your opponents, it's useless to provide you more information, unless it's really, really different. Okay. Finally, I'll talk about the last point. So far in the framework, we've assumed that we're the only player who's strategic. Other players are just doing some, not really optimization, but acting according to our predictive process that I explained. But in reality, it's fairly possible, actually, it's true that players are strategic. So what if everyone is strategic, or a subset of players are strategic? Can we optimize that system? Or maybe can we find some equilibrium in that system? That's pretty much it from my side. Thanks for listening patiently.
We're now going to do the Q&A, so if you have any questions, just raise your hand and we'll come around with the mics.
Did you, when you were predicting how opponents would pick quarterbacks, did y'all take into account popularity? Because that would be one thing. Because I know, like, Ben Roethlisberger is a very popular quarterback, and he would be more likely to be picked just because of his popularity and his history.
Yeah, so great question. And I believe that's totally relevant, and there should be an explicit feature content for that. So we had a feature that predicted these probabilities as point estimates from one of the websites that essentially tries to account for a lot of things like popularity, what's the expected performance. So that was one of the features. So we didn't directly have anything saying what's the popularity of Ben, but we had a feature trying to cover that. But if you can directly estimate that feature, I think that'll be a good predictive tool in this model.
Hi, thanks for the awesome talk. My question is about how do you do your P&L calculation in terms of, do you take into account transaction costs? Do you take into account how you're impacting the market by placing those positions?
Sure. So transaction costs and how, if I'm impacted. So there are no transaction costs in fantasy sports. The only cost is of you submitting an entry, a portfolio. So let's say a simple example is you want to submit a portfolio, and the contest has set rules. If you want to enter this contest, a portfolio will cost you $1. So if you're submitting, say, 50 portfolios, that'll cost you $50. Yes, we took that into account. Other than that, there are no transaction costs. And how we affect the overall P&L in the overall market, I mean, when we calculate the P&L, yes, we take that into account. So if two of our portfolios are coming first, say, they both won't be winning the top prize. One will be winning rank 1, and the other will be winning rank 2. And there was a question about how do I calculate P&L. That's just using the stochastic models we have. So the athletes assume they have a mean mu delta and variance covariance matrix. And the opponents, I had the Dirichlet model. And that essentially lets me simulate the whole system. So I generate a lot of simulations of the system, and compute the expected value of how my portfolio is performing versus how the other portfolio is performing.
So you mentioned the other talk that did the talk, I think, a few years ago at Sloan about this, and I was actually there at that. And what they had the most success with is hockey, where there's significant factors that affect the scoring, such as lines in hockey, and you're more likely to get an assist if someone on your line gets a goal, and goalie wins. So I wanted to talk to you about, if you expanded your model to other sports, how do you think taking into account the unique scoring system that DraftKings have would affect your model based on something like in hockey, lines or the goalie wins are such big factors in terms of how many points your lineup scores. So I wonder how that would change your model.
So my intuition about hockey is that there's low variance in hockey. So it directly ties to the issue of high variance in football. And there should be value in still predicting your opponents. It's just that with low variance, actually, you should see even the expected P&L should be the same, but your standard deviations that we saw were too large for football, they will shrink. So it'll probably take less time for you to actually make more money in expectation. Did you have a second question, or?
So then, do you think that it's much more profitable then to do a sport like hockey where the variance is low? And if so, why did you start your model in football versus something that would be expected to have lower variance?
So to begin with, we didn't really know the variance issue in football. And also football is the most famous fantasy sport. So we thought that if you're doing it, why not just do for football, where first it's most popular, and because of that, there's tons of data available for football easily. For example, if you want to estimate the variance covariance matrix for athletes, in football, that is relatively straightforward. For other sports, you might need, there might be data, there might not be data. You'll have to search for that data.
And that concludes Q&A. Thank you, Raghav Singhal.